that's just that. And then x is less than 2.
Q number 43.
Sure.
Yeah, so this is an open graph, but because we're closing that, it's open. Yeah. So this is open, this is open. So it is going to be because that's the above statement. The above graph that shows. This is covered by x equals 0. So this is yeah, so
All right.
x equals 0.
Okay, 41 through 43, the directions say find the numbers at which f is discontinuous. At which of these numbers is f continuous from the right, from the left, or neither? Sketch the graph of f. Okay? So the f we're given is a piecewise function, right, Giselle? So I know that y equals x plus 2 is continuous for negative infinity to 0, right? Because it's a polynomial. I know y equals e to the x is continuous on the interval 0 to 1 because it's exponential. And I know y equals 2 minus x is continuous on the interval from 1 to positive infinity because it's polynomial. Right? So I know those everywhere on those intervals is continuous. I have 3 places to check, or 2 places to check then. I have to check at x equals 0 and at x equals 1. Those 2 places we still might have a discontinuity. Okay? So for this, if it is to check for continuity, I need to show the limit as x approaches a of f of x is equal to f of a, right? That's what I need to show for continuity at the point x equals a. So let's start with 0 first. So to do the limit as x approaches 0, this is a piecewise function. So I'm going to have to look at what happens from the left and then also what's happening from the right and check to see that those are the same. So from the left is just the limit as x approaches 0 of x plus 2. So if I use, that's a polynomial, so I can just use a direct substitution, make that 2. And from the right, that's the same thing as the limit as x approaches 0 of e to the x. That's continuous, so I can do a direct substitution there. So that's 1. So I know that the limit as x approaches 0 of f of x does not exist. Therefore, we are discontinuous. At x equals, 0. Right? Chanel?
Sorry, may I go to back?
Sure, go ahead. So far, so good? Okay. Now let's look at x equals 1. So again, piecewise function. So I'm going to have to check the limit as x approaches 1 from the left, as well as x approaching 1 from the right. So from the left, that is the same thing as the limit as x approaches 1 of e to the x. Again, that's continuous, so I can just do direct substitution. That's e. And then from the right, that's x minus 2. Or I'm sorry, yeah, x minus 2. 2 minus x, thank you. Yes, 2 minus x. Again, I can use direct substitution because that's a polynomial. So I get 2. Those disagree. So I know that the limit as x approaches 1 of f of x also does not exist. So we know that we have a discontinuity at x equals 1, or 1. So far, so good? Now, I'm really kind of over-explaining here, but I hope that's okay, right? Okay.
Isn't it supposed to be 2 minus 1? So 2 minus 0?
Oh, yeah, thanks. Not that it matters, but yes, 100%. Okay. So the other thing that it then asked is, okay, we have discontinuity, but at those discontinuities, do I have continuity from the left or the right or neither? So what I'm going to need to check is f of 0, because if f of 0 equals the left-hand limit, I have continuity from the left. And if it equals the right-hand limit, I have continuity from the right. If it equals neither, then it has neither, right? So to do f of 0, the directions say to do e to the x. So that's 1. So that matches here, right? So that is continuity from the left. Yes. Yes. And the same thing over here, I'm just going to do f of 1, which again, the piecewise tells me it's just going to be e to the x. That matches the left, or the left limit. Oh, I'm sorry, this is not from the left though. Giselle, this I meant to put right here, right? Because that was the right-hand limit. Oopsie daisy. So again, we have continuity from the left at x equals 1.
Did it just tell us to plug it in the 315? Or do you just
Oh, it's because the piecewise function, right? So when I'm equal to 0 or equal to 1, I'm plugging into e to the x. So yes, it told us to do that, but not like, like you had to see that it, Is that so far so good? Yeah. Now we got to draw the graph, right? And we'll show you what the graph kind of confirms what we're seeing there. So the first piece is a polynomial, right? Or a linear function, even better, y equals x plus 2. So I'm going to use, this is on the interval from 0 to, or negative infinity to 0. So I'm just going to use like -1 and then 0 for my points. So -1 would be -1, 1, and then I'd be at 0, 2. And at 0, I need to use an open circle because it's a less than in the. So there's that piece. And then the next part is exponential, goes from 0 to 1. So at 0, e to the 0 is 1. So I have the point 0, 1. And then I have 1 comma e. So 0, 1. And then 1 comma e. And e is like 2 point something. So that would look like this. And those are both filled circles because the piecewise function has or equal to inequalities on that piece. And then the last one is also linear, so just 2 points will do. These are from 1 to positive infinity, so I'll just do 1 and 2. So at x equals 1, I get the 0.11, and x equals 2, I get the 0.20. So 1120. So it kind of looks like that. So if I look at 0, if I'm coming from the right, let's use a different color. If I'm coming in here from the right, that right-hand limit is equal to the point that it evaluates because we're a filled-in circle there. So that matches what we're seeing here. And if we look at this one coming in from the left, that limit is going to match the point because the filled-in circle there, that's our continuity from the left at x equals 1. Yeah, we don't have continuity here because the limit doesn't equal what the function evaluates to. And same on the other end. Nolan?
So for the furthest left point, like the one you used to draw the, like this part.
This thing?
Did you just plug in a value for x or that?
Yeah.
Same thing for the far.
This one?
Yeah.
Yep.
And you just used like the.
Well, they were linear, so they just straight line
and then
through
for
2
the other
points.
points, you just use the limits.
I used the endpoints. I plugged in the endpoints of the interval,
Oh.
right? And I knew it's exponential, so I know it's kind of curving. So I just kind of faked it.
Oh.
But they're not going to, like the AP people would not be so picky as to, oh, it's too curved. You know, as long as it's curving the correct direction, bending the correct way, I don't think they're going to be too picky about it, especially if it's a non-calculator question, you know, where you're trying to do this by hand. There's only so much you can do. Does that, Giselle, does that feel okay?
Yeah, thank you so much.
And again, I went and really deeply through that so it was clear as to like what you needed to do. That's okay?
Yes.
Okay.
Thank you so much.
Yeah. Others from homeworks. Knowles?
I had 7 written down, but I didn't know how to do it.
Okay, let's take a look.
I think I knew how to, but I wasn't sure.
Sure. Just drawing a picture, right?
Yeah.
I think. Grab that whole block. So it says you want to state a function that's continuous except for the stated discontinuities. Okay. So answers here can vary. It says there's a removable discontinuity at 3. So I'm going to put an open circle at 3 where the graph comes into it and comes out of it. Right?
Yeah.
And then it says a jump discontinuity at 5. So we'll do that. And that'll work.
Just draw the lines any way you want to.
Yes. Yeah. So the lines can do anything you want. Like you could have drawn this line and go, and it's fine, right? It just had to connect into, whoa, where did everything go? Just had to connect in. And again, you could have made this one closed and this one open. Wouldn't have mattered. That's all fine. Bunch of different ways you could have drawn that one, Nolan.
So for removal of this continuity, for some reason I had the open circle.
And you could have had one up here.
Oh.
I think that's okay still.
But that is it.
I think I would count that as a jump, to be honest with you, but
Okay.
I think it's, I don't know. I just leave them all empty if it says removable. Because I think of the, like my canonical example is like, if I have like x plus 2 over x plus 2, you know, that's just going to be like the line y equals 1, but at -2 it has an open circle. That's my like canonical example of a removable, is just like open circle, no extra point. I don't think you should have the extra point. I'm not sure if it's wrong, but I wouldn't put it there
Okay.
for a removable. I would just leave it as, I would call this a jump. I think that's probably still how they're called. I'm not positive. I'd have to go look it up, to be completely honest with you. But I know if there's no point there, it's still removable. So I just, if I don't have to, I would put it there. Katie.
For your top line, like the one at 5, why is that?
It doesn't have to be.
Oh,
Like you could have, it could be like this. That would still be okay. You could have made it like this. That would still be okay. Yeah, any of those would be fine.
Could they both be filled?
Could they both be filled? Nope, because it wouldn't be a function.
Oh, yeah.
It'd fail a vertical line test if they were both filled. But either one or neither is okay. Katie.
I forgot to ask for the last one, but for a piecewise function, you always have to check the left hand.
If you're doing a limit, yes, to evaluate the limit at the boundary of two pieces, you're going to have to check from the left or the right. If we went back to this previous one and we wanted to just do the limit, limit as x approaches 3, that you don't need to, because it would just be the same as the limit as x approaches 3 of the piece 2 minus x. And that you don't need to look at the left and the right for that, because 3 just lives in here, so it's always going to act like this. It acts the same way from the left or the right. Where you get into trouble is when you want to look at the boundary between the two pieces, where one side of that piece acts one way and the other side acts a different way. That's why we had to do left and right limits for this one. Is that?
Yeah.
Okay. These are really good questions, guys. Like good specific, okay, yes, that's why you had to do it that way. Like these are the great questions to be asking, really good clarification stuff. Do we have more about on homeworks?
I think I had a quick one about number 8. It was just the
Okay. Yeah, let's draw it.
thing in -2 where it said neither left nor right. So does that mean -2? Yeah, I guess you just draw it.
Yeah, absolutely. So this is what I would do. So here's -2. And then it says continuous only from the left at +2. So because both ends are open, you can't have continuity from the left or the right, because the function or that point doesn't exist. And even you could have these just one open circle here. You could have both ends going into the same open point. That would be okay. Here we have continuity from the left because the left limit is going to the point and the point is closed, right? That point's there. You don't have continuity from the right because going to the right, the point's missing.
So
Yes.
What if you just drew the one horizontal line? Would that,
Like this?
or even with, does it have to have the arrow at the end there?
Oh, I guess not.
Okay.
I would
Does it
have.
have to go on to infinity?
Well, here's what I would say: is the directions say it's continuous
Oh,
except
exactly.
for the stated discontinuity. So that's why I have the arrows at either end,
Okay.
because I want it to go forever in either direction. So it's continuous except for where its stated exception is. That's why I have the arrow at the end. So I think it's a directions thing. You'd meet the criteria of part of this without it, but the directions you'd miss, I think. So again, it's like one of those make sure we read all the parts kind of thing. But good, yeah, no, these are good questions. Lots of goods there. Okay, should we finish up 2.5 then? Sounds good to me too. All right, so we've been talking about continuity, and we were here at example 7. So let's pick up here at example 7. So here it asks us to evaluate the limit as x approaches pi of sine x over 2 plus cosine x. Recall at this point the big observation that we had made from last time was that if your function is continuous, you can evaluate the limit with direct substitution, right? So that's what I want to check here, is if I can determine that this is continuous, I can just direct sub this in and we're done, basically, right? So I'm going to look at the individual parts. Sine x, is this continuous?
Yeah.
Yes, right? If I go back and I look, it's on my list. Trigonometric functions are continuous over their domain. And what is the domain of sine? All real numbers, right? Negative infinity, positive infinity. You take the sine of anything. Okay? 2, is that a continuous function? Yeah, it's a polynomial, right? Those are on our list. And again, its domain is going to be all real numbers because every polynomial's domain is all real numbers. And cosine, is that continuous?
Yeah.
Yes, and its domain is
Same as that.
all real numbers. Okay, so each of these 3 pieces is continuous. I know the sum of 2 continuous functions is continuous. And I know the quotient of continuous functions is continuous except for where the denominator is equal to 0. So look at this denominator of 2 plus cosine x. Where does that equal 0? Again, this is something we would the AP would expect that you could do without a calculator. Not that you can't look at your calculator, but I'm just letting you know. Christian.
Cosine doesn't go to
Excellent. So the answer is
Nowhere.
nowhere, right? It never gets to 0. What's the minimum output for cosine?
0.
-1. What's the maximum output for cosine? +1. Can I ever get a 0 in the denominator if the smallest thing to come out of here is -1? No, man. So perfect. Can't ever be discontinuous. This is continuous everywhere. Yes. So I can just direct substitute this. Yes, Chanel?
Oh, sorry. So, it's not ever going to be equal to 0. Like, why? Because it's like,
Because the smallest this can be is -1,
okay.
right? So 2 plus the smallest thing possible is still not 0,
Oh, okay.
right? It'll just be bigger than, like the bottom here has to be something between like 1 and 3, because the smallest thing that comes out of cosine is -1, and the biggest thing to come out of cosine is +1. So the denominator can't ever be anything other than 2 plus -1 up to 2 plus +1.
But can't there be a value that causes it to be 0? Because, like, it's in
No.
the interval?
No,
Like,
because it's +2,
oh,
right? Sure, cosine becomes 0 there,
Oh,
but
I
2 plus cosine
it's different.
can't be 0
Oh, okay.
because the smallest cosine could be is -1,
Okay.
and we're always adding 2 to whatever comes out of cosine.
Yeah. Oh, I understand. Thank you.
Uh-huh. All right. Sine of pi.
0.
Yep. Cosine of pi.
-1.
Done. Does the AP expect that you remember your unit circle, sine, cosine, tangents? Yes, they
Last
do.
year.
Yes, they do.
like every single one.
All the unit circle values.
How often will we need them?
Frequently.
Why?
Look, I'm not doing it to you. I'm just the bearer of bad news, right? Here's the thing, though. More often than not, they're just going to be like the quadrantals. You know, like 0, pi over 2, pi, 3 pi over 2,
It's not that bad.
2 pi, like the ones that are easy. And again, I don't memorize these things on the unit circle. I just remember what the graph looks like, right? Like here's the graph of sine. 0, 0, pi over 2, 1, pi 0, 3 pi over 2, -1, 2 pi 0, right? I'm just kind of thinking about what the picture looks like and then just kind of managing from there. I'm not actually memorizing these things because like I have better things to do in my life than memorize the unit circle. I'm just going to memorize what the graph looks like and go, okay, I can figure it out from there. You know what I mean? Because I know what the answers are going to be. You know, like pi over 6 is either going to be like 1/2 or √3/2. Well, if I look at the picture, pi over 6 is like right here. Well, 1/2 is smaller than 3 pi over, or √3/2. So pi over 6 must be, sine of pi over 6 must be 1/2, right? I'm just going to look at the picture and just kind of figure it out. I'm not memorizing them. You can, and some of us that are really good at memorizing things do it, That's not my bag. All right. Very useful theorem. If f is continuous at b, and the limit as x approaches a of g of x is b, then the limit as x approaches a of f of g of x is equal to f of b. In other words, we can push that limit inside of our composition okay. So if we have a composite function and we have continuity, we can just do the limit of the inside and then use that to evaluate the outside. Let's look at an example here. The thing we have to be careful about, though, in using this is that we meet all of these criteria. Well, actually, this is the criteria. So we have to have that the outer function is continuous at the limit of the inner function. So let's look at an example. Oops. So here it says evaluate the limit as x approaches 1 of arc sine, that's the same as sine inverse, remember, of the function 1 minus root x over 1 minus x. So notice here that like my f of x is the arc sine, and like my, is that the same? Yeah, okay, good. And g of x is like this guy, right? So what is the domain of arc sine?
Is it just the same as sine?
It is not the same as the domain of sine. They're inverses.
Oh,
So it's the same as the range of sine. So it is -1 to 1. So as long as my limit as g of x approaches 0 is in this interval, everything is going to be fine. We can just plug in that limit into arc sine and just get our answer out. Does that feel okay to everybody?
Sorry, I didn't understand it.
Okay. Where did we lose you?
Like when you started talking about domain of arc sine, I'm sorry.
Okay. So remember, sine and arc sine are inverses, right?
Yeah.
So sine's domain is all real numbers, and its range is -1 to 1,
Okay.
right? Functions that are inverses, the domain of the inverse is the same as the range of its function,
Okay.
and the range of the inverse is the same as the domain for the function,
So this one
or a
is-
subset of it anyways.
Oh, so the range of this one is all real numbers for
So-
arc sine of this?
The range for sine is -1 to 1.
Okay.
So the domain for arc sine is also -1 to 1.
Okay.
Now the domain for, or the range for arc sine is a subset of all real numbers. It's just -π/2 to +π/2, which we talked about kind of why that was back in trig, and I don't want to go all the way into it. It has to just, it has to do with ensuring it's a function. Because the graph of sine is not 1 to 1. It fails a horizontal line test. So the inverse, if I do the whole thing, is not a function anymore. For us to make it a function, we have to restrict its domain, restrict the domain of the original, and it becomes like a whole thing. That's like too deep of a dive that I want to get into right now.
Okay.
Is that okay?
Yeah, that's
Okay,
fine.
okay. We're okay with where I got to here?
So why did you write down the domain? Is it so?
Because as long as the limit as x approaches 1 of this is inside that domain, I can just plug the answer into arc sine and I'm done.
Is it because it will like for sure recontinue it?
It's because we're just using theorem 8.
Okay.
It's just meeting the criteria for theorem 8. So this is the limit of g of x, and as long as f is continuous at b, And I know that arcsine is continuous over its entire domain, so I just have to make sure it's in the domain.
Okay,
That's all I need to check,
okay.
right? Because the inverse trigs are on our list.
Okay,
Continuous over their entire domain. I just have to make sure it's in the domain, and I'm good.
okay.
Okay? Okay. So, can I do direct substitution on this? No, why not? Well, you get 0 over 0, right? That's one of those indeterminate forms. Shucks. What should I do then? You could multiply by the conjugate. That's fine. That's the natural thing that everybody says on this. There's actually another way you could look at this that's maybe even a little bit easier. When I look at this, what I do is I see that denominator, and I see that 1, well, that looks like 1 squared. And x, well, isn't that the same thing as the square root of x squared?
Yeah.
What's that denominator look like now?
It's like 2.
Like a difference of 2 squares, right? So what I would do, and again, multiplying by the conjugate is fine. It will get you the right answer. There's nothing wrong with doing it. I think it gets a little bit messier than doing it this way, but it is fine. It will work. I just like doing that because factoring, I think, is easier than, at least that kind of factoring I thought was easier than doing multiplying by a conjugate and have to worry about the foiling stuff, potentially. And now this is continuous, so I can just direct substitute it in. So I get 1/2. And since 1/2 is in the domain, this limit is just going to be the arcsine of 1/2. Which one is it? What's the arcsine of 1/2? Unit circle thing, you should have it.
What was the question?
Arcsine of 1/2. Not 0.
Pi over 2.
Not pi over 2. Not 1. Not 2. It's going to be in terms of pi, because the output of arcsine is an angle in radians.
3 pi over 4.
5 or 6.
It's pi over 6. Thank you. It was a guess. Again, here's the way I would think about it. Right? I know what the graph of sine of x looks like, right? This spot here is pi over 2, right? I know here at pi over, what's sine of pi over 4? I mean, it's root 2 over 2, right? Cosine pi over 2, or pi over 4, sine of pi over 4 are both root 2 over 2. That's like 707. 1/2 is less than that. So 1/2, or so the x there has to be somewhere between 0 and pi over 4. The only unit circle angle between 0 and pi over 4 is pi over 6. That's the way I'm thinking about it. I'm not memorizing it. I have to sit there and kind of like draw a picture and figure it out. But it works for me. But if you're a memorizer, like, yo, I'm just going to memorize that stuff, party on, Garth. You know? I know. It feels like a lot. Okay. Yes.
I missed it. What did you do to get from the first part? 1 minus square root of x over 1 minus x to 1 minus square root of x to 1 squared.
So 1 is the same thing as 1 squared, right?
Yeah.
Nothing fancy there. X is the same thing as the square root of x squared, right? I didn't do anything. I just like rewrote it in a way that it looked like a difference of 2 squares, so it'd be obvious to you guys what I should do with it, or what I was planning on doing with it. How, and you say you don't know how I see that, and the answer is, I've been teaching high school math for 16 years. Imagine doing this stuff over and over again for 16 years. How good would you look at doing this kind of work? Really, really good, because you look pretty good doing it your first time doing it, let alone your 16th time doing it. So I see these things instantaneously because it's a lot of practice. That's why it looks easy. It's not easy. Okay. Theorem 9 says if G is continuous at A and F is continuous at G of A, then the composition of F and G is continuous at A. So what this tells you is that continuous function composed with another continuous function is continuous somewhere, right? As long as like the range of the inner function matches up with the domain of the outer function, whatever that intersection is, that'll be where the function is continuous. If there's no intersection, then it's undefined. So let's look at an example here. So we have the composite functions, sine of x squared. So my outer function here, f of x, is equal to sine x. And my inner function here is x squared. Okay? So for the inner function, the domain is all real numbers, and the range is 0 to positive infinity, right? Is everybody okay with that? It's polynomial. Every polynomial has the same domain. Because it's x squared, I know I can't get a negative number out of that, so it's 0 and bigger, right? Chanel.
Wait, so I have two questions. So this is for domain and range of just the polynomial, x squared?
Just for g of x.
Okay, so the range, like, oh, I get it, never mind.
Can't be negative because it's
Yeah,
squared.
it's squared, I'm sorry.
That's okay. Okay, what is the domain for sine x?
All real numbers?
All real numbers. Okay, so let's look at this. I can put any real number in for x squared. I get out 0 to positive infinity. If I plug those in for the x for sine x, is that okay? Can I plug anything from 0 to positive infinity in for sine x?
Yeah.
Yes. And I get an answer back for that, right?
Yeah.
What is that telling me? It's continuous where?
0 to positive.
Yes. No. All real numbers. Because these are our inputs, right? That's what's going into h of x, is all real numbers. What comes out of g, here, let's draw a picture, right? Okay. So h of x, right? That x goes into g. Out of g comes g of x. And then g of x goes into f. And out of that comes f of g of x, right? That's kind of what's happening here. You take an x here. This x is any real number because that's the things you can plug into G, right? Out of G comes the range. That's what gets plugged into F because that overlaps with the domain perfectly. There are no restrictions. So out of this comes any real number, right? So you can, every input is something you can do the sign of, right? I know. Maybe I can draw a better picture than this. Let's try it again. Okay. So this is like my x, and then here's g. So that takes it to g of x. And then here's f. And note that f, or the domain of f, yeah, this is good. All right. So this guy is the domain for G. Let's do this one. This guy is the range for G. Right? And let's do like purple. This guy is the domain for F. Notice the domain for F contains the entire range of G, right? The domain for F is all real numbers. The range for G was all the non-negative numbers, okay? And then the output here is going to be, this is like the range for F. So I was able to put anything in at G, so I can get anything back out at F, because all the way along, the range for G was a subset for the domain of F. And because G is continuous over its entire domain, and F is continuous over its entire domain, and those range of G overlaps with the domain of F, or I should say the domain of F contains the range of G. They're just continuous everywhere. Let's look at one where that doesn't happen quite so trivially. Do something like this. So here, my f of x is the natural log of x, right? What's the domain for the natural log of x? That's incorrect. Not all real numbers is correct. Let me be a little bit more specific than that, though. So remember the definition of a logarithm, right? That just allows us to rewrite this as an exponential equation. So the possible inputs for our logarithm are the possible outputs of our exponential. So if I take some number and raise it to a power, I have to be getting a positive value back from that, right? I can't get zero. Like anything to some power is not going to be zero. And I can't get a negative, right? If I take a positive number and raise it to a power, I can't get a negative to come out of that. Now my g of x is 1 plus cosine x. The domain for this is all real numbers. But what's my range going to be? 0 to 2. How'd you get that, Nolan? So cosine's range is -1 to 1 with the brackets. And we're just adding 1 to it, so -1 plus 1 is 0, 1 plus 1 is 2. Okay? Now let's look at the overlap, or the intersection between the domain for f and the range for G? Is there anything in the range of G that's not in the domain of F? 0, right? So, that's cap F, huh? Cap F of X is continuous everywhere except when G of X is equal to 0, right? Now, we should really find the x's where that happens. What value of x is going to make G of X equal to 0? Pi, very good, because cosine of pi is -1. Now, is that the only time? Also, it happened at 3 pi. What's another one?
5 plus 2 pi, or whatever.
2 pi k, yep, where k is an element of the integers. Very good. Help me if I lost you. We don't need to drop the F-bombs. You can just like slow down. You missed me. Okay? I'm not trying to embarrass anybody. Olden, you okay?
Yeah.
All right. So, what is this? What is that stuff saying? Just in your own words. That's saying when x is pi and everything coterminal to pi, right? That's all that's really saying. Because I know at pi, we have a 0, and we go around another time, we add 2 pi to it. 3 pi, there's a 0. We go around another time, 5 pi, there's a 0. And keep going around, and doesn't need to be forwards, you could be going backwards. So if I subtracted 2 pi, also be getting a 0. But that's all that notation is saying. It's just saying pi and then everywhere coterminal to pi. And I would suspect if this were an AP test, then you'd written pi and everywhere coterminal to pi, they would mark that as correct in words without any symbols. If you just wrote it in words, that's fine. Okay? I would, as a grader, I would certainly mark it correct unless the directions specifically asked for a certain kind of notation. I've never seen that happen in anything I've looked at before. So I think words would be fine there. Chanel?
Have you ever been an AP calc test grader?
Nope, but we talk about it at training, like what grading looks like, because understanding that it helps you to teach the course and what you're emphasizing and the way you get students to do things, right? Okay. That would maybe a little bit better. Last idea here in 2.5 is this intermediate value theorem. This has a name. This one's important. This shows up every year, multiple places on the AP exam. This is one you'll want to have memorized because you'll use it and have to use it like to do stuff. So you need to know what it says. Okay? The intermediate value states that suppose f is continuous on the closed interval from a to b, and let cap n be any number between f of a and f of b, as long as f of a doesn't equal f of b, then there exists a number c on the interval from a to b such that f of c is equal to n. Yowzer, Mr. Kulik, can you translate this for me and what the heck this is saying? Absolutely. And I'll do that in just 1 minute because I see people copying it down. I don't want to talk while they're copying because it's hard to listen and copy at the same time. Yeah. Okay, so let's talk about this. So it says f is some continuous function there, like there's a continuous function, right? And it has to be continuous on some interval from A to B. Maybe let's say that's A and that's B. So if I look at the number f of A, that's the y coordinate, and f of B, if I pick some number n, then there has to be some x on A to B where I can do f of c to get n. Does everybody kind of see what we're saying? Why does this guaranteed to work? Because of continuity, right? If I start someplace high and I start someplace low, somewhere along the line, you pass a point whose y-coordinate is in between the two, right? Has to happen as long as we're continuous. If you don't have continuity, does this happen? Not necessarily. It could, but it's not guaranteed. Okay? Number one thing that students make a mistake when using this on the AP exam is they do not stop to show the continuity before they apply the theorem. You must stop and show that you have continuity before you use the intermediate value theorem. Okay? Other thing worth clarifying, the intermediate value theorem just shows that shows the existence of such a C. It doesn't tell you what that C is. It doesn't even tell you how to find that C. It just simply states that there has to be one. At least one. Could there be more? Sure, right? Like if instead this function did that, then there's bunches of C's, right? There's another, oh boy. I have a C here and here and here and here and here, right? There's a whole bunch of them. But that doesn't matter. All we need to find is one. And we don't even need to find one. We just have to show there is such a C. Doesn't matter which one it is. If there's more than one, less than one, well, there has to be at least one. But don't have to find it. Let's look at an example on how we can use this intermediate value theorem. It says, show that there is a root of the equation, yada, 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 equal to 0 between 1 and 2. So what do we say when we say the word show there's a root of the equation?
Is that like a 0?
It's a solution, yeah. It's a solution, it's a 0, same difference. Yep. Could be used interchangeably for all intents and purposes. So first step, I want to show continuity. So let f of x equal this thing. How do I know that's continuous? Good. And specifically, I only care about the interval from 1 to 2. That's it. I showed the continuity. Just a sentence. That's all it took. Okay. So what I want to do is I want to find two y values where 0 is in between them. So I'm going to track the endpoints of my interval, f of 1 and f of 2. Let's see, what's f of 1? That's 4 minus 6 plus 3 minus 2. That is negative 1. F of 2 is going to be a 32 20 minus 24 plus 6 minus 2, 38 minus, that's 12. Everybody's okay there? My n, my cap n in this case, is what we're trying to get it to equal. So I'll say since f of 1 is less than 0, which is less than f of 2, the intermediate value theorem states there exists a C on the interval from, open interval from 1 to 2 such that f of C is equal to 0. Done. So the setup, I had to show continuity, boom, got it, and have to show there's two y's on that interval where the desired y is in between them. That's it. Did it. Dunzos. Now I apply the intermediate value theorem and it returns me the desired result. Katie. Such that. Sorry. That's a C, f of C here. Does it look like an E? I'll do that. Okay. I have a little bit of bonus composition, limit of compositions examples to do, because there's a specific kind of question that I see appear on the AP exam rather frequently that we have no practice of in our textbook. So I just want to kind of go through some examples of doing this. Okay. And this is where we have a composition of two functions, but you're not given the definition of the functions, but rather a graph. So we're going to do a couple of examples here. So here we're asked to find the limit as x approaches -2 of f of h of x. So the first thing I'm going to look at is my graphs of f and h. When I look at those, the thing that I notice straight away is that they are both continuous everywhere. If that's the case, I can just say that this is going to turn into the limit, f of the limit as x approaches -2 of h of x. So I go locate -2 on h of x. That limit should be 1. That's f of 1. I find 1 on f, and that outputs 1, and I'm done. Or 8, I can't remember which one. It was one or the other. Yes, that's exactly right, Ethan. Let's see, where is it? That's your brother, Christian, sorry. 8 is what we used there. A long time ago, he went here. Okay. All right, next one. Again, what do I notice right away when I look at the graphs? F is continuous, but h of x is not continuous. Now, that's not a problem unless the limit that we're looking for is where the discontinuity is. So if I look at the limit as x approaches 0 of h of x, what do I notice here? Yeah. So what does this tell us about the limit of the composition? Doesn't exist. Everybody's okay there? Okay. Here again, I notice h of x has a discontinuity. So I have to be a little bit careful here. If I look at that limit, that's -3. The limit as x approaches -3 of h of x is 3. And that's okay now because g of 3 is 1. So that's fine. So again, because the limit as h of x existed, and g, the outer function, was continuous everywhere, it was fine, even though I didn't have perfect continuity. Let's look at this. What do you notice here? Yeah, they're both discontinuous, right? Okay, we're still going to start at the inner function. So what's the limit of that inner function at -1? Doesn't exist, right? Left-hand limit goes to negative infinity, right-hand limit goes to positive infinity. So what can I say here? Doesn't exist. It's okay. Here's where they start getting tricky. This is the worst one here. Oops, and I need to type this in correctly. I want the limit of f of x. So, do the limit of the inner. What do I get there? 2, right? Okay. So then who thinks that I would just do then like f of 2? So I should get 1, right?
Do you have to do the limit of that?
That's not right. Why can't I do that? I have a discontinuity at 2, so I can't do that theorem 8 because the limit, it has to be continuous at that point, right? And we don't have the continuity at that point.
2 would be
However, I can still do this problem, but I have to think about it in a different way. So this is what I have to do instead. When I look at the limit as x approaches 0 of f of x, I'm approaching 2, but it's always approaching 2 from below, right? 2 is always coming from a value smaller than 2 leading into 2. So this limit should be the same as the limit as x approaches 2 from below or from the left of f of x. That I can do, it's just 0.
So you can like approach things
When it's a composition,
you
yes.
can approach like y from different spots too, and not just
Well, again, the y is the input for the next function. So that y of the inner is the x for the outer,
okay, true.
right?
Yeah.
Which is the hard part to wrap your head around when you're seeing it for the first time. Chanel.
Wait, so, sorry, can you repeat it one more time? So why is it just 0? Like, is it because...
So if I look at the limit of the inner, we're approaching 2. But we're always approaching 2 from below. We're coming from values that are less than 2 up to 2, right? Now that output of the inner function is the input for the outer function.
So the output is just...
So I can say then, I can look at the limit as x approaches 2 from the left of the outer function f of x, which is just going to be 0.
So I'm so sorry. So you're plugging into the one with that's filled in, the one that's circled. You're plugging in that too, which results in.
Nope, I'm not plugging 2 in at all. That's the difference.
So you're just saying that.
I'm saying, here, let me add a little bit of notation to help make this a little bit clearer. I'm going to put an O here for outer and put an I there for inner. So the inner function is always approaching 2 but it's approaching 2 from below. Always values less than 2, right? So those are going to be the inputs for my outer function. So my limit for the outer function is approaching 2, but from below or from the left. So when I look at that, that's here. Is that?
Yeah,
It's hard because it's F and F.
yeah, I'm just, yeah.
Let's do I have one more example here. But that one we just did is a frequent one I see on the AP exam, and it's a tough one because you want to just do your continuity rule and just do f of 2, and you can't. All right, let's look at this one. We start the same way, right? We'll do, again, we'll call this outer and inner. When I do that, I get 2. But what do you notice? I approach 2 from both above and below, right?
Yeah.
So that means if I want to do the limit as x approaches 0 of the outer, I have to do the limit as x approaches 2 from below. Oops, I should say and then I have to do the limit as x approaches 2 from above. Now when I do that, what do I get when I approach 2 from the left? I get 4. And when I do it from the right, I get 1. What can I say here? Because those two, left-hand limit and right-hand limit, disagree. So the big picture takeaway, let's summarize here this most difficult situation, is if the limit of the inner is at an extrema, and the outer function then is at some discontinuity, you can do that. If it's not an extrema, you're not going to be able to do it. Nolan.
What if though, instead of a jump discontinuity, it was a removable discontinuity, but couldn't you have still done it? Because it would be approaching the same thing from both sides.
Right. Yes. I think that would be okay.
In that case, you could have.
Yes. Yeah, I think you'd be able to do it then. Yeah. You had to have a jump. The jump was the problem.
Yeah.
Katie.
Why are they both F outer?
Good afternoon, Notre Dame. Let's stop where we are and end our day together with a prayer. In
Because
the name of the Father, the Son, and the Holy Spirit. Amen. Please join me in the prayer of St. Francis of Sales. Be at peace. Do not fear what may happen tomorrow. The same loving Father who cares for you today will take care of you tomorrow and every day. Either he will shield you from suffering, or he will give you unfailing strength to bear it. Be at peace and put aside all anxious thought and imagining. Amen. In the name of the Father, the Son, and the Holy Spirit.
okay.
Have a great afternoon, Notre Dame.
Hold 1 second, guys.
You may dismiss, and you are ready.
So, nothing new today, homework-wise, other than finish the end part of 2.5 if you didn't look at that stuff with the intermediate value theorem in it. I put some more stuff on my AP. I really would treat that more as test review stuff. So you can start looking at things and doing parts that you feel like you can do. But if you don't want to look at anything yet, you don't have to. If you haven't done the 10 multiple choice questions from before, please do those by next time. We need to talk about those in next class because we haven't done that yet. And then we have to do 2-6 next week and probably a review day and maybe test the week after. Tentative. Chanel?
Are these questions of accuracy, the cluster field questions?
Okay, Katie, let's talk, because you had the question about the outers and inners.
Oh, I think I'm good now. Is this one -1? Because it's right here.
No, it's probably this.
Uh,
That one about now.
So here's what's going on, right? If the inner one is going to 2, I can replace this limit of the composition with just the outer going to 2, right?
Wait, what?
So here we have the limit as x goes to 0 of a composition, right?
Yeah.
So if the inner part is going to 2,
Like this whole thing.
We're gonna do 2.6.
so if the inner part's going to 2, I can ditch the insides and just write the outer part going to 2,
Okay.
which is what I did there.
Okay.
Now here, I have to worry about, because it's a jump discontinuity at 2, I have to do a left hand and a right hand.
Okay.
So here, from the left and from the right, we're approaching 2 from values bigger than 2 and values smaller than 2. So I have 2 plus and 2 minus, or I'm sorry, 2 minus and 2 plus. So if I can sneak that in there, make that a little bit nicer. So when I look at approaching 2 from the left, I'm coming into here, so that's the point. So 4.
Oh, yeah.
And when I'm
And then
approaching
coming
2
right
from
is
the
one.
right is this
Oh.
point, which is 1.
Not looking at the one on the y-axis.
Okay.
Is that? And this is all
It's on
on
the one.
OneNote too. But yes, you're welcome. And picture anything
Yeah.
you'd like.
Okay, thank you
Does
so
that
much.
feel
Yeah,
better?
That makes a lot more sense. Thank you.
Yeah, of course.
Have a good day.
You too.